So we'll start. So today we're here to talk about cloud native Java, and are you and your company ready for cloud native Java? My name is Charlie Gracie. I'm the garbage collection architect on OpenJ9 Java VM. Oh yeah, I forgot we had a picture of this here. You can reach me on Twitter, GitHub, anywhere if you want questions afterwards if we don't have time here.
I'm Jamie Lee Coleman. I used to work on the Docker team for WebSphere, and I'm now a developer advocate. And again, you can reach me on Twitter if you need me.
So, quick quiz. Who here has been deploying Java applications for years and is all ready to move to the cloud? And if you are, what are your approaches? You decide it's so different, you're just going to throw everything away and rewrite it from scratch? Have you decided the cloud's just sort of a small thing, bury your head, wait for it to pass by, and then keep going with your big apps? Or you're going to understand how modern Java runtimes may actually help you in this new era of cloud to reuse and take advantage of the things you already currently have. Anyone here doing any of those three things?
So, hands up for A? No. Hands up for B? No. Hands up for C? You've got to have one answer. All right, cool.
All right. I'm hoping everyone had their hand up for C. That's what we're here for. So what's really so special about the cloud and running things on top of your runtime? So the cloud is, and everyone talking about it, makes all kinds of great promises, but it's very dynamic. You don't have to have all of this hardware yourself. It'll scale quickly. There's minimal costs up front. There's just a ton of things here that everyone's making promises about, but, oh, and the compute on demand, just always what you've always wanted. It's just cloud will save everything and is going to make developing and working on your Java applications or whatever you happen to be working on easy and perfect. That's great, but the big thing that everyone sort of really leaves out, especially if you're talking about Java and things like larger runtimes, is that in the cloud, all of your compute equals money. It's a cost for you, and it's a constant sort of cost all of the time. It's not your hardware anymore, so you're paying somebody for the rights to this hardware. And within the cloud, and this compute equals money, really that translates down into dollars per gigabyte of RAM used per hour. That's kind of the main way that everyone is charging for the cloud. Of course, there's different things for numbers of CPUs and stuff, but the biggest and most broad one that you see across all the different cloud vendors is how many gigabytes of RAM are you consuming per hour. Which means in the Java world, the size of your heap is really costing you money. It's an easy translation. So changing the size of your -XMX, you can literally see a difference in the cost you have per day, per month, per week that you're running in the cloud. So if you look at a normal workload here, it's great hand-drawn art. Everyone can see my artistic skills. So the demand of your application may go up and down over time as you're going through how many transactions, how many customers are hitting your website. But and how does it really react to this different movement and different amount of resources hitting it? So the way this is normally handled is you have one big server running all the time. It's able to handle everything. You over-provision it a little bit so that it can handle extra transactions and an extra increase. Tuesday on Netflix, when their new shows come out, they have extra demand, so you over-provision everything for the worst case. Basically, everything above the white line, you're wasting that resource most of the time. So if you have this VM running with a 2 gig heap and most of the time you're using less, you're paying for 2 gigs of heap in the cloud, so that's actually a huge waste on you. You could actually go and make some smaller times, bring it up and down, change your heap, so then you're really only wasting at certain times. You can make it smaller again, but there's still always a lot of waste. So if you look at this one, oh, can't figure out how to work it anyway. So over here, so it's just throwing out memory and throughput. So when you're ramping up an application, you'll notice that it takes a while to get to maximum throughput, and that you'll see your memory usage go up as the application is starting up. And there's always this sort of spike at the beginning, particularly when you're looking at a Java runtime. That's early on when the just-in-time compiler and things are kicking in, compiling lots of different methods for you to have faster throughput. That's why your throughput's getting faster. But they'll have these spikes and peaks of where they consume large amounts of memory. So in this model, you see that the cost here and extra times are till you get to your maximum throughput. And then also you have this over peak usage of your memory at that point as well. And any of the time that you're not running fast as you can and you're using more memory, you're paying money that you shouldn't have to pay. So this is more like what everybody would like. Almost instant on, no extra memory, always using the amount of resources. But we're going to talk a bit about how maybe we can get there. So in your cloud demands, one of them is that you want a small memory footprint. As you scale out more and more applications, say in like a serverless or a microservices architecture, you have multiple JVMs where you used to have one. So any overhead that the JVM has itself is now multiplied out. And then as you spin out more instances of that, you spin it out even further. Everybody wants a small deployment size, and you really want this scaling out, so you want a very fast startup. If you need to handle more transactions or more customers, and it takes 2 minutes for your new instances to spin up, you've probably just timed out or lost some customers. Things took too long, they left. So can we do all of these things and make these improvements with a JVM? Is the cloud so different for the JVM? Another little quiz for everybody, keep everyone awake. Is the JVM no longer relevant? A, yes, it's irrelevant. We should all move to Node.js. B, maybe we might be able to tune it and these types of things, but it's going to be difficult. Or no, all the JVMs are the same, and that's what we got. So hoping again, everyone's not picking A on this choice, but we'll move on. So my answer to these things is OpenJ9. This is a new-ish VM that was open source and donated to the Eclipse Foundation in September 2017. It's a completely open implementation of the VM. It uses EPL v2 and Apache 2.0 license, so it's free to basically use for whatever you want, has a very non-restrictive licenses. We're always looking for new people. Come check things out, open pull requests, open issues. If you don't get an immediate answer, I'd be surprised. Ping me personally. I'll get you questions answered right away. To get OpenJ9, it's just a VM, but if you want the JDK as a whole, I recommend going to get all of your JDKs from Adopt OpenJDK. It's a program build environment run by the London Jug. They build OpenJDK with Hotspot, with OpenJ9, all different releases. They're building nightlies, building releases. It's a great place to go get your binaries. And you could then make some easy comparisons because they're built on the same sort of cadence and timeline as well. So it's a very easy way to know what you're getting in your JDK package at any one time. Sometimes when you're pulling it from like apt-get or something on Linux, you're not quite sure which really release, what else has been done to it. So these are some very vanilla ones you can go pick up as well. Of course, every build they do, they also create a Docker image for it as well, push out new versions of Docker images based off of this as their Java. So you can go get those as well from Docker Hub. Why is OpenJ9 so good for the cloud environment? The world's greatest phone of all time was actually running Java ME. And some of these small phones were running OpenJ9 at the time. So the roots of OpenJ9 come from a very small embedded VM. So with that, the JVM Java ME requirements at the time were very small footprint. Lots of times you had very little RAM. You had large amounts of ROM sometimes, but you had this very small amount of RAM you could use. You have to have a very quick startup. People's games, which was mostly the use of Java on these phones. Again, 2 minutes to start up your game. You're not playing the game very often. It's too annoying. And you also don't want your game to only play well after you've played it for a while every time you start it up. Like you just don't want it to be responsive 2 minutes after it's JITted everything. You really want that to happen early on so you have a consistent gameplay. Those look very similar to the cloud requirements. Small footprint, you want as close to instant on as you can. You'd want a really quick ramp up time, just for the fact that all of these things as you go through cost you money. The more time you're not doing your peak, the more money you're paying for no reason. So some sort of quick results here using OpenJ9. I have some links and things I can share and I'll tweet later. You can go get some Docker images and things and do a lot of these tests for yourselves and follow some of the simple steps. But startup time with OpenJ9 using our shared classes technology and this option quick start, basically you can see that it's about 30% faster. Mileage will vary here. Everyone should test on their own. Don't always have to take my word for it. Check things out yourself. And the big one is footprint. On a lot of things, when you measure, just out of the box, switching from hotspot to OpenJ9, 60% is kind of one of the average amounts of less footprint you see. 50 is the number I put on a lot, but the more we gather data, more people are tweeting about things afterwards. That's really what it's closer to 60%. So right away, you could cut your cloud costs in half for a lot of applications. Save your company money right away. So if we remember this slide from before where I said this is sort of the ideal where we want to get to with memory footprint, if you look at it, so using one of these same tests was using OpenJDK 9 with hotspot. This is the memory consumption over time. And here we go, is OpenJDK with J9, the JDK 9 one. So we actually get the, this one's actually throughput, sorry, not memory. So you actually get to peak throughput actually quite a bit quicker with OpenJ9. If we run with OpenJ9 using our AOT technologies, which you get by using that share classes option I showed earlier, just putting that on, you'll get this pre-compiled JIT code in your cache. You'll actually see that you basically have this instant on max throughput for what you'll get for max throughput using only AOT code. Since it's not doing all of the heavy JIT optimizations you could do, you're going to be somewhat limited here in max throughput. And it makes, even though it still does continue to do some JITting afterwards, it makes some decisions early on based on the decisions it made before to do it quickly that kind of sort of limit you. As the releases keep happening, this number, the green line and the blue line, keep getting closer. With our last release, it's quite a bit closer again. Just those builds weren't ready before we came here to put them in the chart. They're just being built this week with the latest release. And those will continue, hopefully, to close the gap as we go forward. But it's just a decision you can make, again, as another alternative to actually get there even quicker, depending on where your max throughput is. But if, say, you run an application that only ran for 2 or 3 minutes, you were never getting to the peak throughput in either hotspot or OpenJ9 before anyway. You were probably actually lower or around the same as what the AOT one could get, and you had that right from the beginning. So that may be a trade-off you're willing to make, depending on what your application's doing. So just sort of to cover things a bit quickly here, OpenJ9 has always been really designed to be small. We've become the SE JVM as well. So it now works on small memory, and it scales all the way up to really large, powerful servers with terabytes of RAM and hundreds of CPUs. It can handle these constrained environments quite well. And a lot more things have been coming online as of late as well for like auto-detecting that you're in Docker images or other types of virtualized environments and enabling things like idle detection and some of these to turn off a lot of the extra things, re-give memory back to the OS when you're not using it. If your image has gone idle, why do you still keep this memory committed? Shrink down to your current working set size, hand that back to the OS, and you can grow again if you ever need the memory again. So these types of things are all coming online and being done in OpenJ9. So for me, I'm saying that the OpenJ9 JVM sort of saves the day here. It's something that we're really hoping that a lot of people will try and look at. Again, it's got this really great license, so anyone can contribute and use it for whatever you need to use it for, and it's there. And again, don't take just my word. actually, if you look and search on Twitter for the @OpenJ9 tag and just in that user account, there's tons of people talking about this regularly, about just like the bottom one here, like just switched it and I dropped from 300 megs to 130 megs of my memory size, and they kept their same or slightly better perf. So I'll now move on to Jamie.
So, thank you, Charlie. So cloud native Java. Are we done? Yes, there's nothing to see. Let's move along. Not really. I still need to re-architect my application. Or no, actually cloud native introduces some new challenges. So hands up for A. Good. Hands up for B. Or hands up for C. So the correct answer is C. Yes, you do have to re-architect your application, but it does create a lot of new challenges. So what you can run on your JVM can outweigh the benefits. That is true. You could have the best JVM in the world that could start up as quickly like OpenJ9, but if you run something that's very heavy on top of it, you're going to not get any of the benefits in the cloud. So let's have a look at Enterprise Java. May 1998, it started off as one project. Then we had 10 specifications, 13, 20, and now we've got lots of specifications in Java EE. I'm going to quickly talk about OpenLiberty. So this is something that you could run on your JVM. It's a very, very lightweight application server. It's a new open source project. I say new, it's been around about a year now from IBM. The design goals of this application server were to be efficient. So it starts up quickly, very low footprint. It's only about 100 meg in size. I've managed to get about 10 of these running on a Raspberry Pi, all in Docker containers. So that's a $20 piece of hardware. So that's how small it is, really. Simple to use. We wanted to go from what we had with traditional WebSphere to create Liberty and then OpenLiberty, and we wanted to make it very, very simple to use. So you can configure the whole server in one small XML file. Consistency, I want to be able to deploy this anywhere and I want to be consistent every time, so that was another thing we had to consider. Just enough application server. We don't want to have this big application server, especially when in the cloud. When we scale up things, we don't want to be scaling up these big application servers that are 5, 10 gigabytes in size. So again, we get the features we want from Java EE or microprofile, and then it builds up, we have our application server just as small as we need it. Good for virtualized environments. We have Docker images for this application server. We have ones for microprofile and for Spring. End of migration. We don't want people to have to move to a new version and then have to change their code. We want it to just work. And Agile ready, very quick startup times. You can literally get this application server running in about 10 seconds. So this is simply how you configure it. Feature manager, you just select the features you want. The packaging type here, Minify, will squash the server down as small as possible, and Runnable will put it into a runnable jar for you. So here's just an example of some Maven dependencies. So that's how you would configure Liberty with Maven. And here's an example of Thorntail, so very similar. So you've been deploying Java applications for years, and you want to move to a cloud-native approach. Do you decide cloud native is so different that you need to throw everything away? I know we've already approached this slide. Do you decide that it's just a storm, you're going to hunker down and wait for the clouds to pass? Or do you understand how modern Java runtimes let you reuse and extend your existing code? So this is the big thing about microprofile, is it allows you to build on the knowledge you already have. So everyone who's got knowledge of Java EE can very easily use that knowledge with microprofile. So not all cloud native challenges can be solved by the runtime. So traditionally, and IBM has done this in the past quite a lot, is where we've had very big release cycles, so once every 6 months, it gets to the last 2 weeks of that release cycle and your infrastructure is hammered. Everyone's running builds, everyone's trying to get their code in, and basically your infrastructure all of a sudden grinds to a halt, and you have to pay for this very expensive infrastructure because you have to handle that peak load. So this is why the cloud is great, because when it comes to right at the end of your development cycle and those 2 weeks, you've got this cloud which you can just pay for the extra resources for those 2 weeks. So like you were saying before in your earlier slide, you don't have to pay for all this computing power all the time. You can just pay for it when you need it. Agile in microservices helps get code to production a lot easier. So you actually don't need these release cycles anymore. There's a product in IBM called Message Hub, and they do this so well. They do not have release cycles. Every day they produce their code, it gets built, and it goes straight to production, and that is a daily build thing. And it works so well. It means that we don't have to have this time of the month where all of a sudden all our infrastructure is hammered. So you have to think about when you develop microservices in a slightly different way. And it also helps having all your services separated, because then you don't have to do a massive build to redeploy your whole application. You can just do a build which for this microservice, again, reducing costs on infrastructure. So Eclipse Microprofile. I presume you've all heard of Eclipse Microprofile. This conference has been very microprofile centric. Microprofile came around, I think it was around 2016. Basically, the industry wasn't going, Java EE wasn't going fast enough for us. The cloud was already here by that point, and we kind of knew the way forward was using the cloud. So a lot of vendors came together. There's actually a few more like Microsoft now, to basically create their own specification for microservices. So there's a good chance you'll use REST APIs. When they were thinking about how all these services are going to communicate with each other, we needed a way to have these services decoupled. Otherwise, it defeats the point of microservices. I love WebSockets. I think they're great, but unfortunately, that reduces very strong coupling between your services. And REST APIs and HTTP requests seems like a really good way to provide a solution for that. So Eclipse Microprofile, at the beginning, we had a look at the Java EE spec and decided these are the fundamental things for microservices. REST client, dependency injection, JSON P for parsing JSON, JSON B for basically turning an object into JSON and convert it back into an object again, so you can share that object between your services, and JAX-RS. But then all of a sudden, handling hundreds of collaborating microservices, and they're evolving all the time, we can't just use those APIs, and that's not enough. So then came along, Microprofile added its own APIs. So configuration, essentially, you've got these hundreds of microservices. I don't want to go in and configure each one of these microservices. That is a pain in the bum. So basically, configuration allows you to externalize your configuration. So for example, a Docker container, you could mount in your config. You can change it, and that could change configuration for, say, 10 or 100 microservices. It also works dynamically, which is great. You can actually change things while your application is running. JWT, so JSON Web Tokens, they were already a standard, and they work very well with HTTP requests, so that seemed like the obvious choice for security. Fault tolerance. So fault tolerance, we need a way to make sure that if one of our services is unreachable, we have a fallback. So Netflix does this very well. So their recommendation service, the bit at the top which recommends shows to you, that is personalized to your viewing habits. Now, if that goes down, do we really want a big black bar there, or do we really want Netflix not to work? No, we need a solution for that. So fault tolerance essentially allows you to put a little annotation at the top of your methods to give it another method to fall back to. So then we can have another microservice. So for example, Netflix has a recommendation service, a generic one that's always sitting there. And if their main one goes down, which is customized to you, then Microprofile allows you to then fall back to this generic microservice. This happens quite a lot with Netflix, but the users do not know that is happening. All they see is the recommendation service is still working and it's recommending some shows to you. You have no idea that is no longer tailored to you. So that is why fault tolerance was introduced. And then OpenAPI, is basically allows you to have a common set of APIs for your vendors to use. So you're deploying microservices that depend on other teams, and you've noticed some errors in their service, and it's caused your service to fail. So what do? Do you blame the other team and tell them they need to sort out their act? Do you hold firm and just sit there and wait and trust that eventually they'll fix the problem? Or do you take responsibility for gracefully coping with instabilities in the services? So hands up for A. That's cool, that's fine. Hands up for B. Good, thank you. And hands up for C. Awesome. So personally, I would go with A and C. I would take responsibility for coping with these situations, but then I would also go back to the team and say, you're lucky I coded the way I did, because otherwise our service would have gone down. So personally, I would have gone with A and C. So yes, now we've got to handle hundreds of collaborating microservices, and all of a sudden we have to consider things we never had to consider before. All these services are communicating with each other over a network, and with monolith applications, we never had to worry about that before. So hence the introduction of these three. Open tracing allows you to see exactly all the requests that are going between your services and the responses from the services. So it allows tracking requests to be made a lot easier. Health check is pretty much what it says. Microservice, are you alive? Yes, good, here's the request. Microservice, are you alive? No, okay, I'll fall back to something else. And metrics basically allows you to get certain metrics out of your microservices. So you can see the heap size, you can see how much memory you're using, how much CPU usage you're using, and you can even put custom metrics in there very easily. So you can put metrics in there for anything. How many times has this method been called? How many times have I had to fall back? How many retries did it take to hit a microservice? So with metrics, you can pretty much customize it any way you want. So you're the proud owner of a live production microservice, but like me, I like my weekends, and I don't like to sit at a computer the whole weekend resolving issues. So do you decide it's a no-op due to encapsulation? The great thing about microservices, that's you never need to know what's going on inside. Do you write everything to stdout? X-Factor, the 12factor.net tells you that's all you need to do. Or do you instrument your services with health and Q probes, metrics with Prometheus, and use open tracing with Zipkin? So hands up for A, good, hands up for B, hands up for C. Cool, yeah, so definitely C. Basically, if you put all that into your microservices, you can figure out what's going on very, very quickly. Whereas if you didn't, it's going to take you a long time to debug these things. So everyone probably thinks, well, why can't I do all this with a service mesh? Why not? I mean, Kubernetes does a lot of these things. Yes, Kubernetes does. It does the retry and the timeout and the circuit breaker and the bulkhead, but Kubernetes does not offer anything in terms of fallback. If I can't hit my microservice, I need it to fall back to something like Netflix does. And that's where this comes into play. Now, you can mix and match. So you can use Kubernetes for the top 4, or you could use Kubernetes for one of the top 4 and have your application do the rest. It's entirely up to you, but unfortunately, your service mesh does not solve every problem. So packaging for deployments. I'm pretty sure, well, as far as I'm aware, I haven't come across a cloud that doesn't support Docker. Docker, basically, in my opinion, Docker has pushed microservices to where they are now. Docker came around, I think, just before MicroProfile. It made us look at the world in a different way. So before, we had these big monolithic applications, and when you start sticking them in a Docker container, all of a sudden it doesn't make as much sense as it once did. You've got all these Docker containers all communicating on the same network, so why don't you split your application out? So I'm going to talk a little bit about layers. So this is bad, this is good. I'll explain why now, because Docker is very, very good at sharing layers if they are the same. So for example, here, it would share the OS layer, it would share the JVM layer, but this layer won't be shared because now you've got this big fat jar. Whereas if you had 2 of these, you could then share the application layer, which would bring down the size of your Docker repository, and it also makes startup time of your Docker containers a lot faster. So your boss asks you to recommend an open technology stack for deploying microservices. Do you recommend Eclipse OpenJ9 to optimize your runtime characteristics and cost for the cloud? Do you recommend MicroProfile to add resilience, monitorability, and more in a vendor-neutral way? Or do you recommend the right-sizable runtime with a broad open spec support, open liberty? Yep. Or all of the above? So I'm going to start with D. Hands up for D. Hands up for C, B, A. Okay, so yeah, correct. One of the things is here I want you to take away from this is vendor neutral. So Spring is very easy to learn, and you can get up and running with Spring very quickly. But you are locked into one vendor, and that vendor has control of everything, which is a really, really big problem. If they decide to make a decision you don't like, tough, you've got to deal with it. Whereas MicroProfile has so many vendors inputting specs into it and inputting their ideas that it's very, very difficult for basically something to happen without your input essentially creating issues for you. Also, you're not locked into one vendor for support. You can now go to multiple vendors to get support, hopefully, which will bring down your costs a little bit. So I'm going to show you a little bit of fallback code just to show you how simple it is to do this. We have a website, openliberty.io. There is loads and loads of guides on here. There's some OpenLiberty specific ones, but then we have loads to do with microprofile, fault tolerance, there's stuff to do with JWT. Some of them are interactive, which is quite nice. But for example, this is fault tolerance. This is all you need. All you need to do is that one import and that annotation. And basically all that does is basically say, if this fails, fall back to another method. And here's the fallback method. So essentially what Netflix would do in this situation, this fallback method would go call another service. And that's how simple it is to do fallback in microprofile. Also, I'm going to show you a little bit of how to do config. Here's my config file. It's just a .properties file, and I've got stuff in there like a port number, is in maintenance, so you can change booleans to true or false depending if you want to like stop requests going to a certain microservice if you're doing maintenance. That could also come up with a message saying, oh, this website's in maintenance, try again later, something like that. And then to import that, all you have to do is this import here, and then simply inject the config like so. And now that config will be this integer here will be the port number from your configuration. And you can also do this dynamically, so while your application is running, you can change the configuration and your application will pick it up instantaneously. From me, I think that is it. Here's some useful links. So we've got a link to so there's a link to the OpenJ9 site, there's a link to the Adopt OpenJDK site where you can get all the new versions, microprofile.io, the Eclipse microprofile site, the website I just showed you with all the guides on, and the OpenLiberty website. And that is the end of our presentation. Thank you. Yeah, do we have any questions? Sorry.
Yeah. The OpenJ9, is there OpenJ9 for every Java version?
Right now available, there is OpenJ9 for Java 8. 9 and 10 are in maintenance because they're no longer releases. 11 and I think 11 is the last one.
I think for the older, but because I had a problem, I used Java 1.6, the application used, and I have to call it to the cloud. So I want to ask if there are older versions that I can use for that.
At Adopt, there's nothing older than Java 8.
Okay.
And what OpenJ9 source code that's open sourced works, the same source code works from 8 and every release newer. We build all the same binaries from it, but it doesn't support anything older than 8.
Yes.
The release cycle of OpenJ9 looks like?
Basically, for comparing OpenJ9 to the OpenJDK releases, the goal is to be same day, but it's more likely to be same week. Right here?
Last time I looked at J9, it wasn't OpenJ9. It had some incompatibilities regards to the names of crypto classes. Have you fixed that?
Which?
So you couldn't use the IBM one as a drop-in for the auto JPEG because some crypto classes were given common IBM instead of common Sun and blah, blah.
A lot more of those have been all resolved now as it's open. I don't want to say all of them have been, but if you did encounter another one that's still there, something like that, it should have been resolved. Because like the last one I can think of was Java Lang Management APIs. We've now implemented those all in the right namespace and things have moved. A lot of that actually got resolved for you by, if you're in Java 9 or newer with modules, because a lot of things had to be listed as JDK internal. So they ended up in exactly the same namespace at that point for those ones.
Any other questions? Yes.
Yeah, there's something I don't understand about this, for instance, the ahead of time compilation. If I run this JVM with the Docker container, it starts every time fresh. There can't be any persistent knowledge of a previous run. It doesn't communicate with other instances.
So there is.
Sometimes from these stories I get the impression that some stuff is shit out. What's happening there?
So there's really two big solutions for that. So one that is not my normal recommended solution is you can actually map volumes when you start up your Docker image. So you can map a volume and have that to be where your shared memory is. The other alternative, which is usually what I recommend to people, if you're building your own Docker image because you're having something installed with your application as well, as part of building your Docker image, when you're building your application layer, if you're doing it in layers that way, then as soon as you're done with the install, I would have it actually run the application once so that it actually creates the shared classes cache for you, and then it becomes part of your Docker application layer. Yeah, you'd have to do it once. Otherwise, otherwise you would lose it every time, like you said. And one more here.
How much does the classic Eclipse IDE, which client application, benefit from J9?
Faster startup. I use it every day. Sorry, I used it every day until a few months ago when I got a MacBook. Now we have, guys, because OpenJ9 wasn't available on Mac until this last release, so I just haven't switched everything with travel. Don't touch your laptop the week before you present. But I've always, on my Windows laptop, I always used OpenJ9 or the IBM JVM at the time with a shared classes cache, so startup was always quite a bit faster. And similarly, the heap savings for a rich desktop client like that aren't quite to the same because, well, one, if you don't go change your INI file anyway to change some of the settings, you're just going to use more because it gives it more, so we can't go less than that. But even when I did lower it down, I would say it's more on the order of about 20%, 15% of less memory, but I usually am really pushing it hard anyway, so it usually ends up using more. But when I was doing plugin development for a while, I definitely saw some pretty nice improvements to go be able to start up my plugin all the time as I was doing that development, spinning up new images all the time. Here.
One question was memory management and giving back memory to the operating system. So Docker is running on Linux. In Linux, you can only move the break up and down in your memory. So when you want to give back some memory that was allocated above the watermark, you have to move it so you can lower the watermark. So do we have a special memory allocator that also defragments the memory and also CPU memory that comes with that?
Like as terms of the GC for moving things for us to give it back?
But you can't give it back one page to the kernel. You can only move the break somewhere in the memory model. That's how it works.
Yeah.
So you have to move around memory that was allocated later but is still in use and you want to reduce, so you have to move to some place.
Depending on the GC policy, there's different ways. Some of them are like the more region-based collectors, like we have balance, which is comparable to G1 and those types of collectors. It is quite a bit easier, but to do some of these, we do actually end up having to compact the heap so that we can give away the high end of the address. Most of the time we would do that at different times. So one of the major times we do it is when we detected your application is going idle. So at that point, you're not consuming many CPUs, so we will, or hopefully none if it's idle, if we're right. So then we will do a compact and contract the heap and advise it back to the OS. Sometimes we end up having to do that at runtime as well, but usually we try to avoid that as outside of the idle phase. The way we keep it smaller usually is we just actually don't expand. We don't take all the memory that you've given us unless we're spending too much time in the garbage collector.
Cool. Thank you, everybody.
Thanks.
Okay.